Good morning. In today's lecture, we will go through introduction to power electronics. Then we will go to rectifiers and diodes as well. So I already mentioned many times during this course, which is about the conventional or the old science or the old in engineering, electrical engineering, and there is a new or modern electrical engineering. And I mentioned there is a revolution in electronics which affects not only in the computer systems, but affects also on the electrical engineering or in the power systems, affects on the communication into the wireless, etc. That's why we see all of the technologies are growing in the especially last century. We see how is the revolution in the technology, and that's happened because of the semiconductor materials revolution and the invention of the transistors and the switching devices as well. Okay, so let's look, take a point of view into the power system area. What's this, what happens or why, how this revolution in the electronics makes effect into the power system. So, power electronics is basically a topic in electrical engineering which is associated with energy conversion and power control with high efficiency. So this allows us to apply these technologies in many applications in electrical engineering. So as a shortcut, power electronics, sometimes we call it as PE, then it can be used for energy conversion. Energy conversion like what's the conversion between DC and AC. So we can convert the energy from DC to AC, or we can do the opposite, AC to DC. We can make it between DC to DC, then AC to AC. Okay, so using the power electronics devices, we can, at any time, any points, if we need to convert the DC to AC or AC to DC, that will be fine. Let's recall when I discussed about the differences between AC and DC, and I said right now, since we have a high voltage or something called HVDC or high voltage DC, for very large distances, like 1,000 miles or above this distance, we can use HVDC for transmitting the power. If it is below than that, then we need, we need to use AC. So to convert this to AC, how can we make this conversion? Using the power electronics device, which is DC to AC or AC to DC, whatever more convenience. Also, one of the most practical application about DC to AC, the renewable energy. Renewable energy, especially in photovoltaics. So we call it PV. So as we know, the renewable energy is where the energy sources can be generated. We call it green energy, not from fossil fuel, like the solar converting the lights energy into, or the lights into electricity. Wind convert the wind into electricity. Hydro convert the water or the ocean or whatever into the electricity, convert these forces. So, for example, the photovoltaics, the power is being generated in DC. So how can I connect this photovoltaics and make this power useful, or connect this to the utility grid, or to be useful to our home? We need to connect an DC to AC converter, which is sometimes we call it inverter. By connecting the inverter device, so I can make this power useful, which is, since it's DC, I need to convert this to be in AC, 60 hertz 120 volts or 240, whatever I need. So I need to use a device, and that example, which is DC to AC, or in other words, the inverter. How about AC to DC? What's the practical using for this? Sometimes we used to call it as a rectifier. And this can be used on, like the chargers. For example, battery chargers. And battery chargers can include your cell phone charger, your iPad charger or tablet charger, whatever. It can be used on your laptop chargers. It can be also the PC, because most likely the electronic devices are working based on DC. Sorry. Then we need to convert this from AC to DC. Electric vehicles chargers as well. Whenever there is a battery, the battery must be in DC. There is no way for the battery to be in AC. In other words, we cannot store the AC energy into the battery. We can only store the DC. How can we store this or connect this to the battery? Again, using the rectifier, or we call it the power electronics device, which is AC to DC. So we see that these technologies make a really great revolutions, which is the battery chargers. If there's no power electronics, even if there's a revolution into the computer or the revolution into your cell phone device will work on fuel instead of working on the batteries, because there is no way how to charge the batteries at that time. Or how about your laptop? How can your laptop work without energy? So you need to have energy source. And these energy sources, you need to have a tool how to store it or how to discharge it, charge it or discharge it. So you need to have everything about this. And even like with renewable energy sources, with the invention of the power electronics, we see that the renewable energy sources can be significantly improved. However, in the past, or the early invention of the renewable energy, it was used, some of them for watering, for heat the water, but not to be as direct energy or direct electricity. But now we see that, so nowadays it's been more used, and we can see it around us nowadays. So we realize that, okay, or we found that by the revolution of the power electronics, this allows us to do many things. Then how about DC to DC converter? Why do I need to use DC to DC converter? It's already been in DC. Why I need to make it another DC? It actually can be used as step up or step down of the voltage. This one practical example. What's the point? Why do I need step up or step down? For some applications like HVDC, for example, you need to have it from low to high or high to low, something like that. So someone can say, we already have a device that can step up or step down, which is the transformer. So why do I need to use power electronics if the transformer can do the job? Do you have an answer for this?
Smaller?
Small?
Like,
Yeah.
I don't know, transformer. My mind's bigger than a DC to DC converter.
It can be, but there should be one or another answer that can be more accurate. So, do you have any idea why the transformer cannot be used in DC? Or why we are using DC to DC converter? Most likely, it is because the transformer works only with AC. You need to keep this in mind. Works only in AC. In other words, there is no way to use the transformer in DC. Otherwise, there will be something wrong happening with it. Was this something wrong? Recall the transformer, the circuit, equivalent circuit of the transformer includes inductance, right? Recall the transformer, it used to be like coils like this and core. So these coils are basically inductance. And recall the inductance in DC will be what? Short circuit, right? The inductor in DC will be short circuit. So this will affect into the transformer, which make it overheats. and will make the transformer something we call it saturated. So this saturation in the transformer and the overheat will make it most likely it will not work, of course, and it will harm the transformer as well. So there is a certain amount of current that can handle it for DC. After this value, it will no longer working well. And even if you remove that DC, it will still not working until you disconnect the transformer and reconnect it back, or like turn off everything. It's because there's something related to the magnetization of the transformer. So this will affect. I'm sorry. Okay. Then the transformer, since the equivalent circuit of it is related to the inductors and the DC inductors short circuit, this will make the transformer unsuitable for step up or step down of DC. It can only work with AC. So the best case to make step up or step down using power electronics device, DC to DC converter. That's why I said nowadays with the invention of power electronics, we no longer say that we cannot control step up or step down the DC voltage easy. In the past, when I start discussing about the AC, I mentioned that the AC wins one of the drawback of the DC at that time, which is we cannot step up or step down the DC voltage easy. Now we can do. Now its problem has been solved. So with the modern technology, this problem has been solved. And we can use DC to DC converter. In addition to this, we can use this to control the device. It's not only about converting DC to DC. It can be, for example, uncontrolled or unregulated DC to make it regulated, which is I have a DC source and I need to control, for example, a DC motor. The DC motor can be controlled based on the voltage. If you make the voltage high, the speed go high, voltage low, speed goes low. So using the DC to DC converter, we can control the DC motor, which is I can control the DC to make the voltage higher, then speed increased. Voltage lower, speed decreased. That's another application of DC to DC converter. And of course, there are too many applications. How about AC to AC? Why do we need AC to AC? We already have the transformer that can do AC to AC, which is step up or step down. Why do I need AC to AC since the transformer can do that job? It's actually not related to step up or step down. It can be related to frequency converter. That's one example. Frequency converter like what? Like 60 hertz, 50 hertz conversion between this. As we know, the systems can be either 60 hertz or 50 hertz. For example, in the US, it's 60 hertz. In Europe, it is 50 hertz. So let's assume you purchase a device in Europe and you want this to be working on in the States. So what shall we do? How can we make this device working? You can purchase basically a frequency converter or a frequency converter. Yes, this is the conventional name, which is basically converting the frequency from 50 hertz to 60 hertz. The frequency frequency alone is not enough, because the voltage in Europe is 220 or 240, whatever, while the voltage here it's 120. So you need to have a frequency and voltage converter. So you need to have this, then you can convert your device so your device can work, for example, here in the States. Or if you already have your own device and you travel to Europe and the voltage there is 220, what shall we do? How can we make this device working? Basically, you can use a frequency converter with the voltage as well. Then it will make it from 220 or 230, 240, whatever, to 120. And the frequency from 50 hertz to 60 hertz. So basically, we can use AC to AC converter, which is using the power electronics devices. Now, the question is there, so as I said, like here, the United States, we are using 60 hertz, in Europe 50 hertz. Is there any country in the world that are using two systems or uses 50 hertz and 60 hertz at the same time? Have you ever heard of a country in the world that uses two systems, 50 and 60? Actually, Japan. So Eastern Japan works with 50 hertz, while Western Japan works with 60 hertz. Why? It is maybe because at the early invention or the early connection of the electricity, the east and west of Japan were kind of far away from each other. So there was their own standards with Eastern, their own standard with Western, and they were not connected at all. Nowadays, with the development in the country, and they are going like the electricity goes everywhere, so they are now connected with each other. The east and west are connected. But how? We have 60 hertz and 50 hertz. How they are connected? They are connected using the power electronics devices. They are connected using the power electronics, which is basically we have AC to AC converter. We have 50 hertz at this side, we have 60 hertz at this side. So we can connect east to west easy. And in real life, sometimes we use AC to DC converter, then make it DC to DC converter here, then DC to AC converter. Sometimes they realized when we make it like this way, it will be more efficient than using AC to AC. But whatever, the equivalent circuit of this one will, of course, will be AC to AC, because DC with DC will cancel each other. Then we realize that, okay, we can, no matter if what's your system's working, then that's fine. It's not a problem. If you purchase any device, we can design a converter for you, then it can work wherever where is the part in the world, it can still work. So we can just connect that device or design that device. But sometimes the problem is related to the cost. Is it really feasible to make that device for you and build this device for you and give it to you? Then you can run the system or run your device. Or maybe it might be cheaper to just get rid of this device and buy a new one here. So it depends on, is it cheaper or not, or on other factors. So in summary, what the power electronics uses, they can be used in computers. They can be used in battery charger. I'm sorry, pardon me. Battery chargers. They can be used in variable speed drive of motors. Recall the synchronous speed 120 F over number of poles. Now we can control F using the power electronics devices. Then let's recall, go back when I said about the synchronous motor, it works only at constant speed application. Now it's no longer true. It can work at any speed by using the power electronics devices. So let's go back a couple lectures in the past. So I said the or the synchronous motor works only at constant speed application. Now it's not true. It can work at any speed that I want using the power electronics devices. So we see that some problems that we used to have in the past are no longer exist. It has been solved using these devices. Basically, you need to have an extra device. It's called power electronics. And actually, it's not only related to the frequency. It can be used to control any motor, which is the power electronics devices. Sometimes, like even when you have the servo motor, when you have some other motors, when you are controlling this using the Arduino, you will see that most likely you will use I'm not sure if you are familiar with Arduino or familiar with motor controls. But in case if you are familiar, you will see during your code, you will use something called pulse width modulation or PWM. This kind of pulse width modulation or PWM will go to the power electronics device. Then that's sometimes we call it drive circuit. Then this will be used to control the motor. So you will see it everywhere, in your charger, in the motor controls, and the computer, the renewable energy, battery charges, so, and also in renewable energy. Renewable energy, integration with grid. So when I need to connect the renewable energy sources to the grid, the photovoltaics, for example, it's DC. I need to make it AC using power electronics device. The wind speed, wind turbines, it has. I'm sorry. The wind speed, it has a different variable, or it has a variable speed because wind speed can be changing. This makes the wind turbine changing speed. So we can use the power electronics with the generator, so we can make it regulate these devices. So we can connect any renewable energy sources into the grid in an easier way. Then we can use this also in a grid interconnection. With different frequencies. So now if we have several countries that can be connected in electricity, it can be connected with power electronics devices, and that can be fine. Okay, any question about this? This is just as an overview about the power electronics. So I just want you to let you know that the modern technologies can solve a lot of problems that we used to have in the past. So when I discuss about the motor in the past, I used to discuss the conventional or the old science. But now with the revolution that happens in using the power electronics devices, now these problems solved. Then we have many different analyses other than what we discussed in this class. We have different analysis or modern analysis to deal on, to make the design or to make the control or different calculations. So what we discussed in this class in the past or the previous lectures, it was the old science, it was in the past. But now there are a lot of modifications, a lot of challenges happen, change happens. Let's go back to the notes. Here I'm gonna just go through some applications that for using the power electronics. Look at here the laptop charger. I think I missed the R. Laptop charger. In the laptop charger, most likely you need to look at the data sheet. It is, as we know, the battery is in DC, the wall outlet is in AC. So we need to convert AC to DC, and also the voltage in the wall outlet is 120 volts, while the battery sometimes can be 5 volts, 15 volts, 20 volts, whatever. So how can you make sure that this laptop charger works with your laptop if for example, if you purchase not the original one, like some commercial laptop chargers, and you need to replace your chargers? How can you make sure that this charger is suitable for your laptop? Basically, by looking at the sheet. Look at the sheet here. We see that, look at the input and outputs. Or the first point, look, is it, if you're, you need to replace it with, let's assume this is the original model for your laptop charger. I need to purchase another one cheaper than the original. Maybe the original sometimes can be expensive. I need to purchase a commercial one. So the first step, look, is it the same wattage or like adapter? So for example, if you have 90 watts, is that one is the same as 90 watts adapter or not? This is the first observation. The second observation, look at the outputs. Is the outputs the same voltage, the same currents? If yes, then you're good to go. Okay? That's how we can realize that this charger can work with my either cell phone or can work with my laptop, with any electronic device, by looking at the outputs. If the outputs, for example, 20 volts, and your, for example, cell phone is 5 volts, this will harm your device. So don't use it. That's very important way, which is by looking at the adapter wattage and look at the outputs. Okay. Now, let's assume you already have this adapter and you travel to Europe. Do you need to purchase a converter so it will make the frequency 50 hertz and will make the voltage 120 volts or 220 volts? Actually, it depends on your device. So what I encourage you is to look at the data sheet or look at the label. So when you see this label, let's just look at this laptop. Here, you will see 100, 240 volts. What does this mean? It can work at 100 volts, 120 volts, 200 volts, 160 volts, whatever. This device is capable with different voltages. It's capable to work with different type of voltages. Then 1.5 amperes. Then you see 50 hertz, 60 hertz. What does this mean? We can say this is universal, which means it can work in the United States, work in Europe, in any part of the world, no matter if the frequency is 50 or 60. It can work with any frequency. If the voltage is 100 volts up to 240, it can work without harming your device. It can still work functioning well or actually functioning perfect, which make it universal. That's why sometimes we call it universal. Therefore, that's actually the vast majority of the laptop chargers. You will see this one, which is it works with 50 or 60 hertz. So I encourage you to look at your laptop charger and see if your laptop can work with the different frequencies or not, different voltages. If yes, that's fine. The only thing that you need to worry about is the plug, because the plug can be different with each country. And that plug adapter is just easy to find. There's a universal plug adapter that can work. But the purpose of the plug is just to change the shape so it can enter the wall outlets. It's not about the power at all. The power, your laptop device is still working without any problems. Okay? Clear? The other thing, which is the electric vehicles chargers. So when you look at the electric vehicles charger, you need to look at the outputs, input, outputs. So here is an example, which is, you can say that the inputs, for example, can be between 208 or 240 volts AC. It can work with 50 hertz, 60 hertz. Okay, so how can we make it, since here we have 120 volts, how can we make it, let this electric vehicles, for example, device working? Basically, by connecting, instead of phase A to neutral, you can connect it with phase A to B, which is 240 volt system. Okay? How about if you travel to Europe? Okay, it can still work, because in Europe, sometimes it can be 220 volts, 230 volts, or 240 volts. So it can work, no problem, without any problems. And we see that 50 to 60 hertz. And there is another tool with a slower charge, slower time, which is using 120 to ground. Then you can plug it with the normal wall outlet, and it can be fine. But keep in mind, it will be slower. So here, just to show you, sometimes look at the data sheets or the label to make sure that is this device compatible to work with different part of the world or not. So before you travel, when you have your electronic devices, make sure that look at the labels of the charges of all of these electronic devices and make sure if it is suitable, then that's fine. Just make sure that you have the adapter. If it is not, then you need to worry about, okay, when I travel, how can I run this device? But most likely, again, in the vast majorities of the electronics, we are trying our best to make it universal. So the laptop, cell phone, like iPad, tablet, the chargers, any other chargers. We are trying to make them as universal, so they can work either in any part of the world. That's why, again, we call them universal. Let's look at the cell phone charger, 5 watts. This is one example with Apple chargers. So this is the old one or the small one. That's the small adapter, 5 watts chargers here. I encourage you to look at the label here. When you look at the label, you will see the inputs 100 volts, 240, which make it universal, and 50 hertz, 60 hertz. Therefore, this device or this cell phone charger can work any part of the world, and that's fine without worrying about, okay, it's not working, different frequencies, different voltage. No, that's fine. And it's called 5 watts because 5 times 1 equal 5. 5 watts. V times I, 5 watts. That's it. That's why it's 5 watts. Because as we know, the power in DC, V times I, which is 5 volts times 1 ampere. So whenever you need to use this charger to any cell phone, make sure that the cell phone that you need to charge it, which is compatible with 5 volts, 1 ampere. Otherwise, there will be a problem. How about the new charger, the 20 watts charger? So the 20 watts chargers are basically, you will see them compatible with universal. It can work any part of the world. And you will see it is the voltage. It can be either 5 volts to 3 amperes or 9 volts, 2.22 volt to 22 amperes. Okay, how can you select this? The charging controller in your cell phone should be able to determine whatever needed. So for example, when you are using your cell phone, if your cell phone is supporting the fast charging cycle, so the fast charging cycle, it will use the 3 amperes. 5 volts, 3 amperes. Then that's why you will see most likely when you use this charger, it will be 3 times faster than the conventional chargers. So within 30 minutes, your cell phone will be from 20% to 80% during this charging cycle, because it will provide a constant current, which is 3 amperes, during all of the charging period, which is letting this work as a current source. After 80%, it will be moved to voltage control, so the voltage will be constant at 5 volts while the current will be changing. So, which make it slower after 80%. Therefore, the 20 watts charger, it's faster than others, but you need to keep in mind that is your cell phone supporting this or not. So if the modern phones, yes, they can support the fast charger, then that can be fine. The old phones, no, so you cannot use it. Then how about the others, which is 9 volts, 2.22 amperes? This can be used, for example, the iPads, some other devices, or the Mac, etc. iMac. So it can be 9 volts because the voltage or the battery most likely is larger than the cell phone. It's based on 9 volts, and the charging using 2.22 amperes, that's the charging currents. This is another example of the applications. Okay. Kitchen applicants like Instant Pots or rice cooker, something like that. When you look at the data sheet, most likely you will see this one supporting only 120 volts, 60 hertz. Or when you purchase one at Europe, 220, 50 hertz. They are not universal. The kitchen applicants are not universal. Okay, what's the point? Why we are using the kitchen applicants, or why it's not universal? It's not like the other electronic devices. There's still electronic device. There are some special like this smart cooker. It's electronics. It has some electronics on it. So do you think we cannot do that? No, we can do that. But what's the point? Is related to the power. The power being used here, 100 watts or 1 kilowatts, or sometimes larger than that. So the larger power will make it the larger device, the heavier device. So if you are using a larger amount of power, you need to use a larger electronics devices, which make it heavier, make it more expensive. Look at the cell phones, 20 watts, 5 watts. Laptop charger, 90 watts, and there are some like 50 watts, 45 watts. So those are very small sizes. So we can put the converters, the power electronic converter can be small size, low cost, so it does not harm to make it universal. And actually it's more convenient to make it universal because you are traveling with this. When you are travel, whatever, in this part of the world, you will bring your laptop, you'll bring your cell phone charger. But in the instant pots, or I'm sorry, like any kitchen applicants, not only instant pot, like any applicants, so it's consuming a lot of energy, which make it, when we need to connect the power electronic device on it or the electronics device on it, it will be larger in size, heavier, or bigger size. Again, larger power, we need a larger devices. When you look at the motors, small motor, small devices. Large motors, large power. Largest, also the largest power. Also, when you look at the electrical equipment, so when you see a large electrical towers, this means very high voltage, very high power. A small tower or small pole, this is low power. So again, the larger power, the larger size. And this can be a burden into these devices, which is because it's going to make it heavier. Then, which is make the instant pot much, or the kitchen applicants will make it heavier, will make it much expensive. So, and actually also there is no reason to make it universal. Why do we need to make it universal? So we can make the own version at Europe with works with 50 hertz, and the own version here in the States that work with 60 hertz. And that can be fine. So how about if you travel? We find it inconvenient when you're traveling, you will bring your kitchen applicants and put it in your bag and go travel with it. Most likely it will not happen while you are doing this. You can purchase one there, and it's actually heavy. So it's inconvenient for someone to travel and have this kitchen applicants with him. Therefore, there is no reason, there is no point of increasing the size, increasing the cost, increasing the weights with no reason. Why do we need to do this? Then this kind of applicants are not universal. So here I'm showing you, just demonstrate you some applications that it can be sometimes universal, sometimes not. How? There are many factors. Again, what I encourage you is to look at the data sheets and see, or look at the label and see if it is supporting difference or not. So, and I showed you earlier how do we see this. You will see like 100 volts, 240, or 50 hertz to 60 hertz, etc. Okay? Any question? Okay. Now I want to go to show you just a demonstration picture. It should be here. Yes, here. So the power electronics uses, it can be like, as we see here in this photo. So we can connect this to utility grid, connect this to power up some devices, DC loads. We can use this also to for the laptop, the TV. We can use it for the fuel cell, for storing energy. We can use it for several factors, several analysis. So this power electronics device will be in the middle. It's just like additional equipment, so we can use it in different ways. Okay? Okay. Now, I said that we can do the conversion AC to DC or DC to AC using the power electronics. So let's talk about the concept, or how actually can I convert AC to DC? How can I make this conversion? AC is like sinusoidal waveform, DC constants. How can I make this? How can I convert this waveform to this waveform? we realize if we use a switch, a fast switch, and here is, let's assume here is the source, here is the load, here is the switch. If we let this switch running only at the positive cycle, and the negative cycle will be off. On at positive cycle, off at negative cycle. So the waveform will be like this. On at positive cycle, off at negative cycle. So we will get the voltage output like this. So in other words, it will be like this, this, this. Does this look like DC? No. We still need to improve this. So we can improve it by adding something like that. We call it H bridge. Then we can connect our load to this one, this way. So in this case, we guarantee to not only take the positive cycle, we will take also the negative cycle, but we will make it positive. So it will be like this. Now, it's better waveform. We don't have zeros, but this really looks like DC? Not really. So what shall we do? We keep the same design, but we add another equipment. Here is the resistor. So we add a capacitor in parallel. So the capacitor actually will charge and discharge. So the waveform, it will go like this way. Here's the voltage. Then since the waveform is going down, it's supposed to go down. The capacitor will not let it go down like this way. It will go down in a small, because the capacitor will discharge. So the regular waveform, I'm going to draw it in a different color. The regular waveform is like this. But actually what's happening with using the capacitor, it will go like this way. Then instead of going down, it will go in a slope, small slope. Then it will go like this way, small slope. As a result, the waveform will look like this. Does this look like DC? Yes, almost. By observing only this parts, let's forget about the startup. Yes, it's very similar to DC. But we see some small things here, small events. These are called notches. And this sometimes ripples. We don't like them. So how can we get rid of them? By increase the size of the capacitor, or by a proper design, we can reduce this. So we realize that if we can convert AC to DC using this technique, right? Okay. Now, how about the opposites? How can I convert? Let me use a good color. Convert DC to AC, which is basically I have this, I need to make it sinusoidal. How can I make it like this way? The first approach, we can use a switch. Each switch, or actually this switch can be turned on and off to reverse the polarity at a specific period of time. We can say like at 60 hertz, 60 times per second will switch. For example, something like that. So we can make this one switch, it's working like this. Then we turn the switch on to reverse the polarity. It will be like this. Then switch like this. Switch off, on, or we can make a combination of switches to make the waveform look like this, which is sometimes reverse the polarity, sometimes keep it, sometimes reverse, sometimes keep it. Okay, does this make sense? Then we created this, and is this AC? It's AC, but it's not sinusoidal. So this is called square wave AC. Square wave AC. It's not AC, exactly AC yet, but square wave. Okay, how can we make it sinusoidal according to our standards? Have you ever heard of Fourier transform? Fourier series? Okay, in Fourier series, recall the square wave is a combination of or multiple of sines or cosines with different frequencies. You can recall Fourier series and see how to convert the square wave into Fourier series. You will see a combination of cosines, like infinite number of cosines, which is like cosine here with different phase shift. Then that's why we will see that their nets will be like this way. That's according to Fourier. Then we need only one cosine from this infinite cycles of cosines. How can we get one cosine from these cycles? Using the filter, filtering this signal, such that I need just one of these waveform to be to pass. The others I don't want them to pass. So again, by filtering these signals. So we can use filter after square wave. Then it will be like this way. Sinusoidal that we know. Then we have achieved our targets, which is converting DC to AC. Again, we used filter. Why we use filter? Because the original signal is already included into the square wave. The square wave is an infinite series of cosines. I need one of them. Basically, how? Use the filter. Maybe I'm not sure if you're familiar with Fourier analysis. So Fourier analysis, most likely, if you convert the cosine or sine, it will be like this as impulses. I'm not sure if you're familiar with Fourier transform or Fourier series like impulses. When you have a series like a square wave, this is for cosine. For square wave, it will be infinites with different frequencies. Then what I need to do is I can implement an electronics or a filter that can, for example, I need to get this signal. So my filter will only include this signal, so the nets will be like this way, so this will be cosine again. How can I create this filter? Basically, this filter can be as a block. But the practical filter, it will not be exactly black because we cannot achieve it. This is just for your information. If you are familiar with Fourier series. If not, then don't worry about it. How can I create this black while I cannot do it exactly in real life? We create, we call it sync, to get this like, to filter this signal, which is sine sync x, which means sine x over x, something like that. So you will see the waveform of the sync, something like that. Then we can capture the signal. Then this sync, after making this conversion from Fourier domain or phasor domain, or call it frequency domain, into the time domain, it will be as rectangular, and rectangular we can achieve it. So it's just like something related to signals analysis. This will be, it's not our topic in this course, but just for information, we can achieve this using a filters. Okay, so what's the common between AC to DC? What's the magic that make it happen? To make AC to DC, what did we use? What's the common factor here that we use to make it happen? Or in DC to AC, what did we use to make this happen? What's that device that makes the revolution? What did we use here? Switch, right? Without the switch, can we achieve this? No. How about this one? We use switches. Without the switches, can this be achieved? No. Without the switches, this cannot be achieved. Therefore, we realize that, or you can realize here that we used the power electronics needs switches. Okay, these switches, sometimes we call them as fast switches. So when I say switches, I don't mean the normal switch, which is on, off. Someone is turning this on and off. Of course, we cannot do that. To get 60 hertz, can we make it 60 times per second? You cannot do that. Switch cycle. Or even, most likely, we need a fast switches, which is sometimes it can be 10 kilohertz, sometimes 5 kilohertz, 20 kilohertz, or it can be larger. 10 kilohertz means 10,000 times per second. And of course, no one can do it. No one can achieve 10,000 times switching per second. So how can we do this switching? We are not using the normal switch that you know. We will use something we call electronic switches. Okay? We will use electronics switches. And these electronic switches allow us to turn it on and off easy way by using the switches. How can we achieve the switches using electronics? What's the switching elements, or what's the element that can make that switching or can work as a switch? So in electronics, let's talk about electronics. So we realize that power electronics need a switches. Switches relate to the electronics. So let's go to the electronics. Most likely, what's the switching elements, or what's the element that makes a revolution into the computers or into the technology? The transistor, right? The transistor, we replace the vacuum tubes into the computers to be by a transistor, and by the revolution of the semiconductor materials with lower sizes, lower costs, and multiple of semiconductor materials in a small chip, then we can make the computer to be smaller size. And this can be done for other factors as well. So in the electronics, we will use a transistor. And what this transistor is basically a switching element. So let's assume look at the transistor, this one example of the transistor. It can be different ways. So this is base, or we can call it gates. Here is drain, or here is source, here is drain. So you can say, if gate is 0, then drain will not be anything, will be switched off. If gate is 1, switch will be on. How? Because the drain will equal to the source. Source most likely will be connected to 5 volts. Source, which is 5 volts, then means switch on. While if it is off, drain will not equal to source, then which makes it equal to 0 volts, and this is equivalent to off. Okay? So it's actually depending on the signal. So I can control the gate signal, then I can control that transistor to be on or off by controlling the gate signal. Whatever, I mean, these information are just for your information. There is, you will not be tested about this, but I want you just to understand what's going on. So the transistors. So the first part, or the first transistors, which is called BJT transistors. BJT transistors are very common and very used actually when it's been invented. It will be used most likely for computers, not for power systems. It cannot be used for power system because it's low voltage, low current, low power. So most likely in power system, we need to have higher currents, higher power. So which is make it kind of unsuitable. Then what makes the revolution? The MOSFETs. MOSFETs has been invented in 1959. At that time, it was with low power and low voltage. Then, in 1970s, it was available in higher power. Therefore, if you go back to the invention of the electronics or power electronics, you will see the motor or the revolution starts after the inventing of the MOSFETs. Before that, there was part of revolution, yes, using other semiconductor materials. But here I'm talking about it make it cheaper, commercialized, available, then we can apply it into a small scale. So the drawbacks of the MOSFET, it will be in medium speed, or the speed is medium. Okay. So what happens with the semiconductor materials revolution? There is another part called IGBT transistor. This IGBT transistor was available in 1990s. And the good advantage of this is fast switching. So right now, what we are using in power electronics devices, either MOSFET or IGBT. These two allows us to use it in different applications. Therefore, when you go back to the literatures, to the references to the books, or to the invention or the applications of the power electronics, you will see most likely many of them starts from the 1990s and after that date. So you'll see a lot of renewable energies. We used to hear about this, or starting from 1990s and so on. Before that, we used to have them, but again, it's not as to produce electricity. They can be used for boiling the water, or like for the water, and that water will go to the boiling and to make it turbine, to make the turbine run, and so on. So that was a different scenario. But to go direct to the electricity, we will see that all of this happens from like 30 years ago and so on. So that's why we see the modern technologies, or especially what happens 30 years ago, is much faster than what happens 100 years ago and so on. In the electrical system, power system, we'll see the renewable energy sources, the fuel cell, the electric vehicles, the batteries technologies, semiconductor technologies, the computers, the programmings, the cars, everything. Like you see, it's like technology revolutions. It happens in all of the sectors of the technologies. So here I'm discussing about the electrical engineering, which is electrical engineering can include the computers as well. So the semiconductor materials we can create in single chip, small single chip, and instead of 100, for example, transistors or 100 logic gates, we can create 1,000, 1 million with a small chip. Then we can make our devices smaller sizes, and also we can make them faster. That's why we can make the operating system has been increased. Like if you go back to the operating systems in the past, we used to have like as Pentium, then Core, i3, i5, i7, i9, etc. When you go also to the RAM, I still remember I used to have 16 bits RAM, then 32, 64, then 1 megabyte, then 2 megabytes, 6 megabyte, or 8 megabytes, 16 megabytes, and so on. So we see how's the technology. Even the operating system. The operating system was based on 8 bits, then or even it was 4 bits, then 8 bits. Then they created 16 bits, and we say, oh, 16 bits was great. Then after that, they created 32-bit systems. Then from 32-bit, they switched to 64. And what we have right now is a combination between 32 and 64. If it is below than 32, it can be considered as old operating system, which is not used at all. So again, all of the semiconductor technologies creates a revolution in different sectors, communications as well. The communications and the wireless technology has been improved, the Wi-Fi, the Bluetooth, then the satellite signals as well, the GPS, even the radio AM and FM, they used to be in the past. Right now, we can consider this as old, like AM and FM, which is because now we have the internet, we have the 5G, we have the like 4G, 5G, and now they're under development, which is the 6G. It should be come soon, 6G. So there are other factors that affects or like the technology, affecting the technology, and I think the technologies we are still haven't reached the peak yet. We have a lot of technologies to do in the future. We have a lot of ideas, and there are a lot of applications that can be done, but most likely it's the lack of fund or the lack of demand. So I can create a product which is you can, oh, wow, that's great, we can do this. So the one of the challenges, which is how to make this commercialized, which is make it with low costs, lower size, and easy to handle. That's the first challenge. The second challenge, after building this product, my target is to get the profits, or the company that will fund my projects, they need a profit, which is they need a customers. They need to make this device desirable for everyone. So how can I convince the people to purchase this device? Sometimes I can get a great idea that can solve a great problems, but this is not commercialized, or no one is interested in this, then this idea will die. So there are a lot of technologies, a lot of ideas, but again, we will see how's the demand, how's the demand, or how's the market will be, or how can I convince the market to get these devices. That's also one of the challenges. So our issues now are not only with the technologies, but also with the funds. And again, that's what happens actually with DC and AC. AC wins, DC fails, because we said that the cost of AC is better than the cost of DC. And that's fine. Then DC ideas at that time has been removed. So AC wins, because the funds was given to AC. And also when you go back and read about Nikola Tesla, about how when he invented the electricity, he also started to make a project which is transmitting the electricity as a wireless electricity, wireless transfer. And he makes some towers, and he creates some ideas to transfer the electricity for large distances as wireless instead of wire. There was a lot of challenges about this. And at that time, Tesla, I think, at that time, he's still able to solve these problems. But the problem why his project has been disconnected is the lack of fund. Because the company that used to fund him, they told him, we no longer want this project to continue. So he stopped his projects, then that project's just disconnected and disappeared, and this project has been removed. And no one's actually know how actually he built that project 100%. So there are a lot of ideas. So there are even like many ideas here. Right now we are interested in the hydrogen fuel. One of our targets, or one of our concerns, is how to store the energy. How to store if you have a lot of generation, or sometimes maybe during the noon, we have a lot of renewable energy. So how can we store these energies that you have or when the energy is cheap, I need to store this energy. So I don't want to run the peak units or run the expensive units. We can store them using the batteries. The batteries, high capital costs, the operation cost needs some maintenance, the life maybe up to 10 years. After that you need to replace them. This will affect the environment as well. Every 10 years there are some chemicals on it. So the batteries are not good option for very large scale. It can be used for small scale, for a home, that's fine. It can be used for isolated farm, that's fine. For electric vehicles, okay. But we have some environment effects or if even like some cost effects, how to store the energy. Then we have a hydropower, which is we have a water at lower and water up, so you can bump the water, go up when you have extra energy, and then when you need the energy, the water go down, and you have turbines in the middle. These turbines will run, so you can store this energy as a water moving up, down. But the efficiency was around 70%, 65%. So which means I'm losing 30% or 35% of this energy, of the stored energy on this part. So which is something we don't prefer. So how can we make the batteries? That's one of our targets. It's not only also about storing the power like this way at large scale. How about the small scale? How can I make the cell phone run longer? How can I make the electric vehicles runs longer? So that's one of the challenges that we still need to work on it. Even if we can get maybe much expensive one, but there's still like some challenges on it. How about in like NASA devices? How can we make these devices run longer? Then there is a technology we are working on it right now, which is called hydrogen fuel, which is basically, as we know, the water can be split, it's H2O, can be split to oxygen and hydrogen. The oxygen can go into the fresh air, that's fine. The hydrogen, we can use this energy of the hydrogen to produce energy, or the hydrogen to produce energy. And it's working now. We can store the electricity into the hydrogen, or something we call it fuel cell, store this energy on it, and use this to supply our devices. We can use this in the electric vehicles. But we have challenges on this one, which is if there's something wrong happening, this will provide a large explosion. So if the electric vehicles was based on fuel cell, on this fuel cell, if there's an accident, it will explode. So how about if there's small accidents, if it goes into where the cell is located, also it will explode. So which is make it dangerous. And also how can we make it safe for you to have it in your pockets as a cell phone, or to have it in your backpack as a laptop or any electronic devices. So there are a lot of challenges. How can we make this one safer as well? That's why I say we still have a lot of technologies are not growing. We're still trying to make research and development on this. And also, I'm not sure if have you ever heard of, we know that there's electric vehicles, there's something like electric RV, electric trains. Now there's also technology, electric airplane. We are also developing this. The electric airplane, you can mix no fossil fuel at all. It can work with the electricity. But the disadvantage of this, which is during the takeoff. How can this take off? Because it will absorb a lot of energy, a lot of currents, which will drain or will make a voltage drop into the battery, absorb too much currents, which affect the battery. So maybe it will fail if it is fail in taking off. So there are a lot of challenges about this. But commercially, or right now, it's not commercially, but it can be available as, or actually they already did achieve this. A small scale electric airplane can fly. But again, it's not commercialized yet because we're still working on it. Okay, so now again, the future trend is to move to the green energy, green technology. Then we can try to get rid of or actually reduce the usage of fossil fuel. At the same time, clean environments. Then using also batteries, or using the vehicles to be as going to the electric vehicles, which is there will be no noise, no smokes go out from the electricity, and also you can higher the efficiency. So when you press brakes, you will not press actually brakes. You will make the motor runs as generator. So the electricity will be stored into the battery, other than go as losses and goes as heats. This losses will go as heat, will affect in the brakes. There is also one challenge of the electric vehicles. When you are running at low speed and you hit brake, you cannot store this energy into the battery. You need to hit the regular brake, or actually the system will do this, not you. Because if it is gonna work as generator or motor, at low speed there will be a lot of problems. So they are still also trying to figure it out. Any question about power electronics? Okay, let's go back to the notes. I think we're already done with the power electronics here. Then there is, I think, chapter 9. Yes, chapter 9, which is, diode semiconductor applications. Okay, so I mentioned in the power electronics, there must be a switching element. And that switch element I mentioned about the transistor. The transistor can be controlled. I can control when it will be on. I can control when will it be off. But here, in this course, we will discuss only one switching element, which is diodes. Diodes is actually a switching element, very similar to the transistor because transistor is switching elements. But there's a difference, which is this one is uncontrolled. The transistor, I can control when will it be on, when will it be off, and I can do this easy. But for the diodes, I cannot do that, which is something, this is the drawback of the diodes, which is I cannot do that. The early invention of the diodes was before the transistors. So the diodes were invented before. So at that time, they cannot control it. And it's actually semiconductor materials. Semiconductor materials, which means it's not conducting or not insulating. It's not conductors, which is not a metal or it's not a rubber. It's in the middle, semiconductor. You know that in chemistry, like the valence. You know the valence, right? So the number of electrons in the conductors of the valence, it can be 1, 2, 3 to be conductors. While in the insulators, it can be 5, 6, up to 8, 6, 7, 8. While the semiconductor, the valence has 4 electrons, which is in the middle. And in this situation, it can be as silicon or germanium. One example of it. It can be some other elements that has the valence 4, but what we have a lot in our daily life, silicon and germanium. Each one has, or these are the combination of the semiconductor materials. It's also for the diodes, transistors, any other electronics, like something called thyristors, MOSFETs, GBT, BGT, or IGBT, etc. So all of them are based on the semiconductor materials. So semiconductor materials will be as germanium or silicon. The vast majority we are used to use is the silicon, but there are some using germaniums, but the vast majority using silicon. That's why we heard about like Silicon Valley, where the vast majority of the electronics or revolutions has been there, because the semiconductor materials are based on the silicon. Okay, so that's it for today. We will continue next lectures about the diodes and the applications of it. Thank you.